Thank you for the introduction, ladies and gentlemen. Thank you for coming today to the conference to listen to my presentation on climate changes. I will talk not too much. I will show you a lot of slides. And I will start a little bit defining what is climate and what are the manifestations of climate, let's say temperature changes and glaciations and smelting of ice and of course the change of the sea level. This will be the first part of my conference, and then we will have a look into the reasons and what controls the climate changes. I call this conference or this presentation Climate Changes, because the climate is changing permanently. So let's have a look to the subject, what is climate? According to meteorology, it's a sum of weather phenomena. Let's say they have different temperatures, humidity, precipitation, and also air pressures to measure. And normally the climate is defined for a certain area in the course of at least 30 years. So this is the point of view of the meteorologist. But we'll see that the climatologists and the geoscientists look further behind to larger periods of time. Because it's important to understand the climate change of today by learning how the climate changes have been in the past, and only then it is possible to predict the future of climate change. Let's say, according to the temperature zones, we divide the Earth in different climate zones, from polar, subpolar, temperate to subtropical and tropical. So there is no global climate. There are only different climate zones which are changing permanently. And according or depending on the temperature, they move in cold periods to the equator and in warm periods to the poles. So this is permanently in movement. And the same is also valid not only for the climate zones which are moving, also the permafrost is moving the same way. And what is important to understand how the climate zones are moving to the north, to the equator, it's important to state that plants like conifers are very characteristic for cold climate. So when there's a cold climate or cold periods so the conifers go down in direction to the equator, and when the Earth is heating up, warming, so they are retreating to the poles, and the broadleaf trees like oaks, which are very sensible to temperature changes, advance to the poles in case of warming and go back if it's colder. What is also important concerning the shift of climate zones, in the mountains, it's the tree line. Trees need at least 3 months of temperatures above 6 degrees. So till this limit, they can grow. If it's colder, they cannot grow. So this is important to state that the tree line is also an important indication if the climate is going to low temperatures or high temperatures. At the moment, as you can see in this little picture on the right-hand side, we have the tree line at 2,100 meters. But during the very cold periods of the Little Ice Age, this was 200-300 meter higher, or between, or let's say during Roman times and the Middle Ages, this was higher. What did I say? No, when it's cold, the tree line goes down, and when it's warm, it's going up. So as I said, we have to understand the climates of the past to understand the climate situation at the moment and have a look into the future. Geoscientists and climatologists use a huge number of samples, like tree rings or drop stones, varves, and very important are ice cores or microfossils. As we cannot analyze or determine the temperature of the past, like with a thermometer, so we need so-called proxies, representatives, or let's say witnesses of past temperature situations. And therefore, there are a huge number of isotopes which indicate what the humidity, the warmness or coldness was in the past. And luckily, in the ice cores of Greenland and Antarctica, we can also determine in the little air bubbles the CO2 content. So we know how the CO2 content was also in the past. So let's make a short trip in time, going back to the beginning of the Earth, 4.5 billion years ago. And you can see already here, we are, okay, the mouse is not, yes, now. We are today here. This is the reference of, let's say, temperature. And you can see in the major time of the last 4.5 million years, 4.5 billion years or 4,500 million years, temperature was much higher than today. And in the past, there had been only some glaciation periods in the Precambrian, which are similar to what we have today. Today, we have the Pleistocene glaciation since 2.6 million years. And you see, during this time, temperatures had almost been lower than today, up to 15 degrees cooler than today. And the past was much warmer. I show this because I want to see, explain you that since about 3 million years, only the North and South Pole are covered by ice. Before that, it was only partially. Let's say at the moment, we are in a status or in times and period of very low temperatures. What you can see here is the CO2 development of the last 65 million years. And you see here this peak of more than 1,500 ppm of CO2. This came with the mountain building processes of the alpine orogeny. You have to imagine the alpine orogeny was from Europe to the Himalaya. There have been a lot of plate tectonic movements and also with the correlated volcanism. So the high CO2 contents come from this volcanic activity. What I show here as well is that due to the high concentrations of CO2, we could also find today the brown coal formations. Let's say excess of CO2 in the atmosphere on Earth is always a good situation for the plants. This activates plant growth. And if the temperature is high as well as it is today, so plants love it. But then when the temperatures went down, the cold oceans waters and the continental ice cover could incorporate CO2. I will discuss this later on, that the oceans are the biggest reservoir of CO2 and heat as well. So when the ocean water is cooling down, it will trap CO2, like it was here during the last 40 million years. And when the ocean water is heating up, as it is now after the Little Ice Age 200 years ago, it's releasing CO2 into the atmosphere. What is interesting to understand a little bit the oscillation of temperatures are these investigations of microfossils, foraminifera. These are little tiny, less than 1 millimeter size marine animals, which can be analyzed through the oxygen isotopes. And in that case, the scientists studied the last 830,000 years, analyzing the O18 isotope and the ratio to the normal O16. And we can see already here that the temperature is going up and down. And by other experience, we know that the difference from warmest to coldest is 10 to 15 degrees. You see these millennia before passed from the moment now till 830 years ago, and the inverse plot of the isotope index shows us the relationship, it was warmer or colder. What is really interesting here already, the scientists defined the so-called marine isotope states, and they are in this time of period 21. And this gives us time periods or cyclicity of about 40,000 years. But you can also see that there are other cyclicities of some 100,000 years and about 22,000 years by mean. These are by mean. I will explain that what is happening in the solar system is not like a switch watch where zack, 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 the minute has only 60 seconds. Now we go in the next slide to the next or the last 450,000 years. And what we see here is where we are today in the Holocene, the current interglacial period. And before that, we had the Amine, the Amine interglacial. So this is the time between two very warm periods. One today, the Holocene, and the other, the Amine, and the other before was the Holstein. Have in mind the Holstein warm period, the interglacial, and we will come back to this time of 300 to 350,000 years. This information is based on isotopic data of O18 isotope from the ice core in Antarctica. And already here you can see that the CO2 is, let's say, sometimes it does not work. Okay. You see where it's written RIS at this minimum temperature period. You see that the red temperature curve is already going down, is below, and then the CO2 graph is following. And you see the other one at Würm, you see the same. Let's say the temperature is already going down, reaching the minimum of temperature before the CO2 reaches the minimum of CO2. So have a detailed look into the last glaciation, the last ice age, which lasted more than 100,000 years. As the names of the glaciations and interglaciations are very regionally changing. For example, the Weichsel glaciation, which is in the Alpine and southern European area, is called
the worm is called in the Alp regions, and the Weichsel is called in the Northern European region, based on the Wisla, your largest river in Poland. What I want to show here is not only that there are different, even temperature maxima between the glaciation. Let's say it's going up and down also within these 100,000 years. And we are talking a lot of biodiversity. Cold times are always bad times for biodiversity. Also, nowadays, the highest biodiversity you have near the tropics, in the tropical and subtropical zone, but in the polar and subpolar regions, biodiversity is not as high. And I want to focus on the Amian with the woolly rhinoceros. There had been also findings of the woolly little bush elephants. They disappeared, and they became then the mammoths and the known rhinos and others, the Arctic continental animals. I also show this little polar bear, my friend the polar bear, because he's hybrid with a brown bear. So the oldest findings are 130,000 years ago. So he mutated from the brown bear living in the north to the white polar bear. And also what is important to show that biodiversity is very hard in cold times. You see the skeleton of the Neanderthaler man or woman, and the Neanderthaler disappeared 30,000 years ago because it was too cold for him. Homo sapiens, with more cognitive capabilities, he was able to adapt to the new cold, living in caves, having nice clothes and so on, and even moving to hotter places. Because during the last glaciation, life was only possible in the villages of the rivers or at the coast side, because in the mountains, at least in our mid-European area, was covered by ice. As I said, the normal old traditional geological names of the glaciations are nowadays replaced by the numbers of the marine isotopic stages. Yeah, here we are. The heat-loving animals, which had been living in Europe, even in Denmark and in Scotland during the Amian interglacial. These are findings on top for forest rhinoceros and forest elephants, which are 120,000 years old. These findings are from the Upper Rhine Valley near Karlsruhe, where I am living. These disappeared, and during the glaciations, the Arctic continental animals came up. The mammoth, the woolly rhinoceros. And just a couple of years ago, they find in Schöning, and this is the little picture on the right side below, they find in sea lake sediments tracks, footprints of rhinos and elephants, and also of Neanderthal human beings. So let's say within the last 120,000 years, there was a real fluctuation of biodiversity. So let's go further into the direction of nowadays. What we see here is the temperature of the development of the last 9,000 years. And the interglacial warm period started about 12,000 years ago. And we see here climatic optimum in red and climatic pessima in blue, which are appearing every 500 to 1,000 years. And the warmest period of our actual interglacial period was already 8 to 6,000 years ago, with temperatures 1-2 degrees above our temperatures. And although these high temperatures, the polar bear survived. What you can see here already are these so-called climatic optima. About 3,000 years ago, it was the Minoan time, then the Roman Imperium and the Middle Age. And nowadays, we have the climatic optima of the modern era. And in between of the climatic optima, you have climatic pessima. And the last one was the Little Ice Age, then the migration time about 1,500 years ago, and the transfer time between Bronze and Iron Age about 2,500 years ago. So climate is changing continuously, which can be proved by the development of the temperatures. Here we see the representation and the development of temperature of the last 4,000 years. We see the blue graph, which is based on proxy or isotopic data of oxygen measured in ice core data or in ice cores of Greenland. And you see the same. You have the Minoan culture, climatic optimum, then the same from the Roman Empire, medieval, and nowadays our modern era. And what is interesting is between these climatic optima, you always have about 1,000 years, a millennium, and in between the cold areas. And the green graph you see, this was done by Professor Humlung. He used the ice core data, temperature development, to simulate what the future would be like. And this is the only way to predict the climate in the future, to have a look how it was in the past and to make some correlation. And so what we will expect in the next 200-300 years will be a next Little Ice Age, a climatic pessimum, like we had already several times. And you see on this slide also that the temperatures are continuously decreasing. Don't worry on the temperatures. These are the minus temperatures in Greenland ice. Yeah. And after that, perhaps in 2,000-3,000 years' time, we will go down to a next glaciation era. So if we have a look back to what happened with the society, let's say the social, cultural, and social economic effects due to these cold periods, with temperatures decreasing 1 to 2 degrees, and this always resulted in droughts, leading to hunger, to epidemics, and hardship and wars. By the way, the excess mortality nowadays in winter is 6 to 1 or even 20 to 1, depending on the region. So cold is killing, not warmness. As I presented earlier, nice examples or bad examples, heavy examples on this climatic pessima are the Bronze-Iron transition period, the migration period, and the Little Ice Age. So nowadays, we are not living only in a interglacial long time period, which will last 15 to 20,000 years. We are also happy that we have a warm maximum at the moment, the climatic optimum of the modern area. So let's have a look what happened in Poland over the last, almost 200 years. Yeah, you see the temperatures are going up in Warsaw, but even in the last century, there had been very cold times in the 40s, 50s, 60s, and the Baltic Sea was, during the Little Ice Age, frozen very often. But in the last century, mostly in the middle of the century, in the 40s. But we know that also there had been other strong winters, and mainly in East Germany and Germany, we suffered from this very strong winters, 1978 to 79, where in East Germany all the lignite or brown coal quarries stopped operating, so they could not produce heat or current and power. So the only power supply in that period and this year was the Greifswald nuclear power plant. So let's have this in mind when we discuss what is coming to us in the future. And also, if you look to the Baltic Sea pack ice, this is coming, perhaps in 50 years or in 100 years, but it will come. And then imagine what the wind parks in the Baltic will do when the pack ice is coming. In the internet, I found a nice note on the night of the 17th of February last year. And they said that in the Southern Tatra Mountains, there had been temperatures above, let's say below 40, 41 degrees. And I'm not sure, perhaps you know better if this is really the lowest temperature ever measured in Poland. But let's say temperatures, as you can see in the graph, going up and down. And fortunately, since the Little Ice Age, we have higher temperatures, because you have to imagine, like in the strong winters of the last century, during Little Ice Age or the ending of the Little Ice Age, the temperatures were even lower. So the Baltic Sea was frozen. Gdansk Sea Harbor, no way to go out of the harbor. And this will come again. So these are our climatic challenges. Here we see a graph of the last 170 years. These are based on global ocean temperatures. And you see, even in the last century, we had periods of cooling twice. Cooling at the beginning of the century, and then in the mid-century, where we also had the frozen Baltic Sea. Then from 1998 to 2014, the temperatures have been more or less stable. And the last years, even if the media say different things, the temperatures are going down a little bit. So we will see what happens within the next decades. Yeah, again, my friend, the polar bear. The polar bear tripled its population over the last 60 years. So he's happy with this temperature at the moment. And there are scientific research works done on the polar bears, and where the polar bear is in regions where the open sea is no ice, where they can go hunting fishes and other animals. So they gained weight of 20 to 30 kilos. So for them, it's the paradise at the moment. And as I said, they survived the other climatic optima. They survived the Atlanticum highest temperature period of our actual or current interglacier. I think I should comment on global mean temperatures. These cannot be measured. They are based on evaluation, mathematical, statistical models. Of course, they are refined, optimized, but even so, you see on this graph about 26,000 meteorological stations where they are placed in the northern hemisphere, where they are in the tropical, subtropical zone, in the polar region. Only in Antarctica, we have not more than 20 meteorological stations, which are, again, close to the seaside. And you see here already the oceans are the biggest surface on Earth with almost 71%. And where are all these measuring possibilities in the oceans? So they are not really representative of these northern hemisphere focused meteorological stations. In this graph, you can also see how old the data is. For example, the black points in Central Europe are more than 200 years old. So it's very difficult to define and come to solid global mean temperatures. Not only for the distribution of the weather stations, also the meteorology changed from analog to digital. If now we can measure temperature exactly by 1/10 of degree, in the past it was half or 1 degree. And also the housing is quite different. Here you see the old meteorological station in Karlsruhe, which is out of operation, and the new one outside of Karlsruhe. Let's say also the location is influencing a lot. If it's in the countryside, villages, I don't know, you said Warsaw has now 1 million or even more, but 150 years ago, it was a village with 50,000 perhaps. So you cannot compare this. And in the big cities, it's even worse. And nowadays, in the big cities like Warsaw, Berlin, Frankfurt, and whatever, Madrid, you have the so-called heat islands. This means that due to the concrete and the asphalt, you have 3-4 degrees higher temperature all over the year. And because in summertime, the concrete and asphalt is also heating up. And this is also very pronounced in wintertime with our heatings. So it's very important. Most climatologists say nowadays, if we want to study temperature changes, don't do it in the cities. Do it outside the cities. And the best situation is using ocean temperatures. Because the ocean waters are buffering the influence of the insolation and other effects. So if we want to learn something about temperature changes, we should do it through ocean temperatures. Nowadays, of course, we continually analyze the temperatures by satellites, but this is since 50 years. So we don't have a long time experience on that. Yeah, and therefore it's interesting to evaluate and check the climate models, what they say, what the temperature will be in the future. And you see here, in that case, temperatures measured between 1979 and 2014. The reality is quite different to what was modulated. And the main problem of the current climate models is that they look too much into the CO2 and not in the natural parameters. Let's come to the glaciations when the weather or the climate is very with low temperatures. Let's say we are at the current situation with almost, let's say, 29% of land and 71% of the oceans. And here in this graph, I also want to focus on the Pacific Ocean. The Pacific Ocean is larger than all continents together. So this is very important for the development of temperature, weather, and climate. During the last glaciation, the land surface was 18% more because all the water was frozen in the poles and in the mountains. No glacier ice would mean that we have the sea level even 50, 70 meters higher than today, what was the normal case in the past. I think it's also interesting to focus a little bit on the glaciations in the mountains. You see the alpine glaciers can prove 8 to 12 cycles of glacial retreat and advance in the last 10,000 years. Here I present the Uhlig glacier data, and you see that at the moment the glacier is 3,000 meters retreated, but during the Little Ice Age he was just down in the valleys. But even so, you see, even during the Little Ice Age, there had been periods of higher temperature. So let's say the pulsating insolation, the sun energy, provokes glacial retreat during climatic optima and glacial advance during climatic pessima. I show these little picture with the tree trunks because this is the way how we can determine the age of the glacial retreat and advance. As I said, the tree line is going up when it's warm, and the glaciers as well. So there are trees growing, but when the glacier is going back again during cold periods, they overrun the trees, and analyzing the ages of the cut trees or tree stumps, we can say when the phases had been. In that case, for this example, they used the lifetime of fossil larches. Another nice example is the glacier near Chamonix, Mer de Glace. And you see on the graphic B that nowadays the glacier is very high again, retreated, the left photo today. But even during the 19th century, the glacier was still going down to the Chamonix Valley, and that was at that time a real touristic attraction. On the little graph, you see also again during the last 3,500 years how the Mer de Glace glacier advanced and retreated. Yeah, Arctic sea ice in summer will disappear. Since half a century, we are told that. Now it's oscillating in the rhythm of 30 to 60 years. And our research vessel, the Polarstern, suffered that almost 2.5 years ago when he was drifting to the North Pole. So the scientists had been surprised that there was so much ice and snow. And when a Russian icebreaker had to supply them with petrol, food and whatever, he spent all his fuel breaking the ice that another icebreaker had come to supply him fuel. So don't worry, the Arctic sea ice content goes up and down. And nothing different is happening to the Antarctic ice cover. We also have oscillations of 30 to 60 years. Here in this graph, we see how between 1994 and 2002, the ice height grew up. Then there was a decreasing phase between 2003 and 2021. And since 2022, it's increasing again. So also glaciation and the glaciers going up and down. What is important, during the last glaciation, we had an ice cover in northern Europe up to 3,800 meters. And this result that due to the ice load, the Earth's crust locally sank down to 1 kilometer. In the Alps, it was just only 2 kilometers thick, the ice cover. And yeah, like the isotherms, lines are changing and shifting from north to the equator. The same is doing the permafrost. Nowadays, the permafrost line is above 65 degrees latitude, but during the last ice age, here everywhere there was permafrost. And just to remember, wild wine grapes only survived at the Mediterranean. So let's have a look to the sea level changes concerning the glaciations, the so-called glacio or static sea level changes during the last 450,000 years. The difference had been up to 170 meters. Again, the numbers are the marine isotopic stadials. And what you see, it is a very similar picture to what we saw before with the temperature changes. And we know that between today and the coldest period 20,000 years ago of the Würm or Vistula glaciation, it corresponds to up to 15 degrees. This is an interesting and important graphic showing the sea level development during the last 24,000 years. What you can see, the cold maximum was at 20,000 years, and the warm maximum is today, and was already during the Atlanticum 6,000 to 8,000 years ago. When the glaciation, the ice age ended, let's say the sea level rise started smoothly with 3-4 millimeters per year. But then 15,000 years ago, there was a meltwater impulse where we had 30-40 millimeters per year increasing sea level, which later on was reducing a little bit to 10-20 millimeters per year. And this part of the sea level rise is the so-called ramp of sea level. And nowadays we are at 2-3 millimeters per year, and this is the ramp. And you can be sure that the ramp will be in hundreds of years horizontal and then going down again. Some examples just to show how the sea level influenced our cultures. Here on the Vistula Peninsula, you see Roman settings, and I think I don't get the cursor doing what I want. Okay, don't worry. You see even in the little graph of this Vistula Peninsula, the old Roman road, which is now 2-3 meters below sea level. And also in Turkey, let's say around the Mediterranean Sea, you have a lot of settlements which are now in the surf zone close to the sea, but they had been constructed when the sea level was 2-3 or even more meters below the sea level. For me, a very spectacular example for sea level rise is this Cosquer cave near Marseille in the south of France. There you have paintings from Paleolithic times. And the interesting thing is the entrance of the cave is nowadays 37 meters below sea level. Divers found this entrance in the 80s. But again, the former entrance of the cave was 80 to 90 meters above sea level. So we have these, in that case, 120 meters of sea level change. This example I want to show you because I want to remember a little bit what gedanks can happen. We have, again, on the Atlantic side, also Roman settlings with, which had been higher in the time of construction. What I want to show is, or focus, is the CS Archipelago Natural Reserve. This is nowadays an island. And geoscientists studied by seismic profiles, by sediments, and also paleoplayas, let's say former sand areas and dunes, that 9,000 years ago, the sea level was about 70 meters below. So if this happens again, and it will happen, I cannot tell you if it's in 1,000 or 2,000 years, the seaport of Vigo will be a river port, and also Gdansk or Hamburg, Bremen, Rotterdam will just be on land, on a river, but not a seaport. And these are the challenges we have to focus. On the other side, in the surf area of North Spain, in some areas, and also in England, you have these sunken tree stumps, which are several thousand of years old. And you can be sure that they did not grow in that situation, but the sea level was much below. And on the other side, rising or sea levels above our situation today, we also can find along the Atlantic. In that case, we see where the geologists, the colleagues, are walking. These boulders correspond to a boulder paleo beach. The surf zone is on the left side where the algae are showing the brown material. So also on the little pictures below, you see the old Amian interglacial sand beaches. So we also have witnesses of the last interglacial, the Amian interglacial, with 2-3 degrees higher temperatures and higher sea level. I also want to focus, let's see, I have to start this way. The mean or the global mean sea level rise cannot be measured. It's also evaluated based on models, on statistics. And there are also non-glacial or static sea level changes, like the compactation of sediments at the coast. And there's also one big problem with tide gauges, or let's say level water, sea level stations in the coast. They are measuring, of course, the sea level rise from the glacial or static event, but due to compaction, what is measured is higher than the only real or static sea level. Another important thing how sea levels can change are the glacio-isostatic compensatory movements. I said that in Scandinavia we had 3.5 kilometers of ice, which put the crust down 1 kilometer. Now he's coming up again. Also in Finland, you can see it. So there we have not the sea level rising. The sea level is going down several millimeters in Oslo or in Oulu in Finland, 6 millimeters per year. And there are also sea level changes due to tectonic movements, due to plate tectonics. And you know, the Circum-Pacific fire belt, where a lot of plate tectonics and volcanism is happening. And if you go there to the Southeast Pacific and have a look to the tide gauges, you see within 1 year there can be differences of 200 millimeter, 20 centimeters in a year coming up or down. And this is due to tectonic movements, and the isostatic, the glacial-isostatic rise of the sea level of 1 or 2 or 3 millimeters is just disappearing in this tectonic provoked sea level change. Yeah, I found some data from Poland. in Vladislavovo, that's the right pronounced, I don't know, the tide gauge say that there are less than 3 millimeter sea level rise per year between, let's say, in the second half of the 20th century. And in Gdansk, we have about 2 millimeter, a little bit less than 2 millimeter. Why the difference between 3 and 2 millimeters? My only explanation is that perhaps in Vladislavov, the sediment layers are also compacting. So the absolute sea level changes a little bit higher than in Gdansk. And by the way, we come back in the next slide to this. 2-3 millimeter per year rise of sea level, and this in Cuxhaven or in the Battery tide gauge in New York, it's the same, 2-3 millimeters per year. Till 2150, the maximal sea level will be not more than 35, perhaps 40 millimeters. And I'm sure it will be less because we are at the platform of sea level rise. Soon it will stagnate and then we are going down again. So there are a lot of units working on simulating the sea level of the future. And you see, these are just wrong predictions based on unrealistic climate models. So this is for me the first part, climate changes, interim summary. Let's say during the geologic history of the Earth, the temperature was much higher than today. Only since 3.5 million years, both poles are ice covered. And during the last 2.6 million, we have oscillating glaciations, long-lasting 100,000 years, and small, shorter interglacial warm periods. Since 12,000 years, we have now the Holocene interglacial, and we already had the temperature maximum 8,000 years ago. So we are going to lower temperature. So second part, this time is running away, but I have to focus a little bit. What are the factors or the parameters driving the climate changes? Of course, the solar energy, not only the heat radiation, the visible light, also ultraviolet, infrared radiation, reaching the atmosphere, the land, and the surface. Then the cloud cover is very important because if there is a huge, dense cloud cover, the radiation, the solar radiation is reflected, not reaching the surface. This is the downstream solar heat reduced by cloud covers. On the other side, if the Earth is also repeating or reflecting certain heat, upstream heat, of course there are some radiation active gases which absorb heat, but it's only the cloud cover which holds back the heat, not the greenhouse gases, as stated. And what we have to state again, the heat absorption of the oceans, covering almost 71% of the Earth, are very important on the development of temperature, weather, and climate. So let's start with the solar irradiation. We have here the solar cycles 23 and 24, and you see the intensity measured in, or analyzed in watt per square meters are changing. Of course, the heat energy is only varying or changing in the per mil range. This is always what the climate panic makers are saying, oh, forget about this, the sun. But already the ionizing radiation is within the 1% range oscillating. And what is more important, the ultraviolet radiation, which has a big influence in the stratosphere, changing oxygen to ozone under the production of heat, they can vary in the range of 10%. I think it's important to say that we are now in the sunspot cycle 25. The maximum was achieved in October 24. And even then, I'm sure here in Poland as well, but even in South Europe, we could see all these polar lights. How is the sun energy pulsating? How can we see that? Since even the old Greek researchers already noted that there's something happening in the sun, but since the Middle Age, it is recognized that there are sunspots which can be seen from the Earth, observed and documented. Within the year of 1760, they started to number these sunspots. And you see, it's going up and down. Now we are with the sun cycle 25. In 2030, it will go down to a minimum. And then the question is if the next one is above the 24 or above the 25 sunspot cycle in intensity. So what is happening in the sun? In the sun, we have nuclear fusions. Two hydrogen atoms are forming a helium atom under production of tremendous heat. In the sun, we are talking about millions of degrees of temperature. And these currents of plasma, they are working like a dynamo, and sometimes they are just exploding, ejecting plasma fontaines, which are also called solar flares. And they have temperatures of up to 7,000 degrees. Normal surface temperature of the sun is about 5,700. And between the solar flares, you have darker spots, the so-called sunspots with lower temperature. And this is what we can see on Earth, these dark spots. You see, within a millennium, within 1,000 years, we have the climate optima and in between the climate pessima. So the 1,000-year cycle is very important, but the basic cycle is in mean 11 years. And the important thing is every 11 years, the magnetic field of the sun is reversing. So within 22 years, you have again the same polarization. And there are other solar cycles which are also important, mainly when we consider the influence on the oceanic oscillations. I mentioned that the oceans are very important for the climate, for the weather and temperature changes. And you see here the ENSO, this is the El Niño Southern Oscillation Index. The indexes also on the Arctic Oscillation Index or the North Atlantic Oscillation Index are always based on temperature, pressure differences, and so on. So they are defined, and so an index is created to see how they change. And I'm sure in the media, you always hear El Niño, El Niño. But there's the opposite, cooling in the Pacific, which is La Niña, the female version of the Spanish name. And here also we are under the influence of the Arctic Oscillation. And you see, this is going up and down. there's no trend. And this oceanic oscillations controlled by the periodic sun fluctuations, energy fluctuations, have an influence also on the extreme weathers. Here you have more than 150 years of development of the hurricanes. And you see, in the last 20, 30 years, they are not increasing. And they are more related to the Atlantic multi-decadal oscillation. Another example is the accumulated cyclone energy. And you see the blue graph is the global one. The cyclone energy of the northern hemisphere is the black one at the top, and the between corresponds to the values for the southern hemisphere. And there's also no trend. We can say it may be related to the El Niño Southern Oscillation, which are similar, but there's nothing Anthropocene made. This is not man-made. It's nature, pure nature. And why do we depend on the nature? Have a look where we are in the solar system. This little tiny Earth, in between the sun with a more than 100 times larger sun and the 11 or 9 times larger Jupiter and Saturn, the big fat planets of our solar system, which are also very heavy. So these gravitational forces, they have an influence on our orbit around the sun. And Jupiter and Saturn even have an influence on these fluctuations of the pulsating sun. So we know that the orbit around the sun is not always the same. We have sometimes an orbit which is almost circular, but sometimes it's a little bit elliptical. So this is called the period of the eccentricity and has a time for a mean value of 100,000 years. Then, here in the template region of Europe, we have the 4 pronounced seasons, winter, spring, summer, and autumn. And this is due to the inclination of the Earth's axis. And this is changing between 22.1 degree and 25.4 degree. At the moment, we are at about 23.4. This is the obliquity, which is the tilt period lasting about 40,000 years by mean. And then the axis maintaining its inclination is wobbling around, and this is called the precession, and the time period is 19 to 23,000 years. Today, and the wobbling and the precession is important if we are in winter or in summertime closer to the sun. Let's say within 1 year, today we are closest at 140 million kilometers or 158 million kilometers farthest away. But during the glaciation times, this difference was, sorry, I read it wrong. Nowadays we have 147 to 152 million kilometers between the Earth going closer to the sun or going further away. This corresponds more or less to 3% of the mean value. But during the glaciations, with a more elliptical shape of the orbit, this is between 140 and 158 million years. And there, the difference is about 12% compared to the mean distance. Here again, I show the old graph. We know already, and here we see clearly 830 million years divided by the 21 marine isotopic stages. that comes out of a periodicity of 40,000. And if we count all the little tiny temperature maximum, about 38, so this comes to the 20,000 years. So this is proven by isotopic data of temperature changes in foraminifers. Have a look to the eccentricity values. It's just numerical, mathematical value. A circle has the eccentricity of 0. And when it becomes more elliptical, so it's going rising. Only when the elliptic is going to be a straight line, we have the value 1. But you can see we are between 0.005 and 0.6 eccentricity. This is the typical value of the Earth's orbit around the Sun. And what is important, during the more elliptical orbits, we always have the glaciations. And when the eccentricity is smaller and we have more circular orbit, which is with less differences between the farthest and the nearest distance to Sun, we have these interglacials. All these data called Milankovitch cycles on temperature development can be evaluated by astrophysics. It's absolutely no problem in the future and in the past. And here again, we have in the violet color the temperature, on the right side the solar irradiance. And you see that fits perfectly. And if we go to the lower graph on the right side below, so we see that temperature development and total solar irradiation development are corresponding. You see this also in the graph of Berner and Strife in their work from 2004. This corresponds perfectly. What does not fit is the rising CO2. It's still rising since the end of the cold little ice age. Within the solar system, or the solar system is part of the galactical Milky Way galaxy, and it's also very important to state that the cosmic radiation also have an influence on the temperature, the weather, and the climate. And the relationship between a number of sunspots or solar intensity and cosmic rays is inverse. Why? The weaker the solar radiation, so the weaker the solar wind, and consequently the solar wind cannot shade the cosmic radiation. And this resulted that more cosmic radiation is coming in, and we see that in the atmosphere the molecules are clumped together and they are forming condensation nuclei, which supports formation of clouds. And when you have more clouds, less solar energy can reach the Earth and cooling occurs. These are results of the last 20, 30 years. Let's say within the last 2-3 decades, there had been a lot of scientific work doing on that. And here you see also that when we have very humid atmosphere, the temperature is also related to the humidity, or let's say to the cloud cover. Mainly the low altitude clouds over the low altitude latitude oceans. And this means in the equator area, the sun is burning very strong. We have the most heat there, and the ocean is evaporating, giving a increasing the humidity, which later on results in clouds. So we have again an inverse relation between temperature and cloud cover. So this is also very important. So normally there should be no reason to mention the CO2, because the CO2, the effect is minimal. Sorry to tell that to you. And the CO2 is no climate killer. It's plant life, plant food. It's colorless, non-poisonous, and we have at the moment a percentage of 0.04%. It's a relatively active gas. I don't want to use the term greenhouse gas, because the atmosphere is no greenhouse. It's open, vertically and horizontally. But the activity of these gases like CO2 or methane are limited to very small wavelength ranges. And concerning the CO2, the absorption capacity is already saturated. So if we double, triple, whatever, have more CO2 in the atmosphere, there is no further temperature increase. I think we will hear this also a little bit later. Okay, and what is important is that plants need CO2. If we go close to 200 ppm CO2 or below, plants struggle for surviving. And if it's below 150 ppm in the atmosphere, plants are dying. And this was also the problem in the last glaciation times. The oceans took away so much CO2, the plants had no food for the photosynthesis, and it was cold again. And it's important to state that when temperatures fall below 10 degrees, photosynthesis does not work anymore. I just want to explain this with the wavelengths, areas of water vapor, which is the most important relatively active gas. This is the turquoise color. And we see in orange the energy ranges coming from sun to the earth. And in blue, these are the spectra which goes again leaving the earth, reflected, the heat reflected by the earth, leaving into outer space. And the only way heat can be absorbed and a little bit stored is the water vapor in this area where the heat is escaping. If you look to the methane and to the carbon dioxide, these are little, very limited wavelength ranges where they support heating. And therefore, this wavelength ratio is called the water vapor window, because only water vapor can take some color, some heat, with exception of clouds. Clouds also stop the heat loss. And I don't want to go into detail into this, but this is just to show the Earth is no greenhouse. It's an open system. At the equator, we have all the sun power coming and heating. So we have a convection cell going up to North Pole, South Pole. But as we have also a rotation of the Earth, so we have also a movement. And the convection cell is not one cell, there are several convection cells. And the way is that near the equator, the oceans are heated up, are evaporating, providing humidity to the atmosphere, which then goes north, and in some places where the temperature is changing, the winds are changing, it's raining, so it's going down. By the way, from the equator to the north, not only heat, also humidity and aerosols, dust is going in direction to the poles. But when the air reaches on these complex air currents, the pole overall in wintertime, the air is dry. There's no water vapor which could absorb some of the heat. So these are the ways how the heat is leaving the earth. A Spanish colleague called this also the doorkeeper of the heat. So just have in mind these difficult, complex air streams, which are also different in January or let's say winter and in summertime, also based on the energy coming in, but also if we are in wintertime or summertime closer to the sun. Heat absorption capacity of CO2 is almost completely saturated. The first 20, 30 ppm of CO2 had been important to increase temperature of almost 2 degrees. But since then, the CO2 has nothing to do with temperature increase. Sorry to that. And again, you see when the plants struggle to survive below 200 ppm of CO2 or extinct below 150 ppm. Yeah, in the geological past, we had CO2 contents of million parts, 1,000 parts per million, let's say 2, 3, 4,000 ppm. And the increase in the geological history was always related to mountain building, to plate tectonics. We have the Caledonian orogeny. Here the mountains are mainly related to the Variscan orogeny, and I already mentioned Alpine orogeny. So in these cases, we had a lot of volcanism. And just 2 million years ago, we had the opening of the Atlantic. So look, the CO2 peak. The good thing is that when there was so much CO2 and the temperature always supporting plant growth, we had forests, tropical forests, swamps, where we had so much biological material, which was the base forming our hard coal of the Thermocarboniferous time about, let's say 300,000 years ago. And also the brown coal is related, as I showed before, to higher CO2 values in the atmosphere. So you have seen how big the concentrations had been of CO2 in the Earth's history, but the Earth always managed to redistribute or to reduce the CO2 in the atmosphere. There is no point of no return in nature. Sorry. Because we have the photosynthesis of the plants, but not to forget the fungi and the algae and also the phytoplankton reducing, eating CO2, consuming CO2 during the photosynthesis. And this is called the biologic pump. The next way to absorb high contents of CO2 is cold water. This is the oceanic pump. And finally, we have a lot of plants and animals cooperating CO2 in the form of carbonates, calcite, in their body. And after that, when they die, we get the nice limestones. Let's say the limestones is nothing else than stored atmospheric CO2 of the past. And I hear very often, oh, the bad cement industry, they emit 8% of the anthropogenic CO2 into the atmosphere. Yes, but what? It's just giving back that to nature. So the most important slide is this of the oceans. They can absorb tremendous amounts of CO2. They are hosting 50 times more CO2 than the atmosphere. The colder the oceans and the higher the pressure going down in the water depths, the more CO2 can be absorbed. This is the famous oceanic pump. And also, to finish with a fairy tale that CO2 will stand for thousands of years in the atmosphere. That's not true. We have the geological pump, we have the oceanic pump, and so within 4 or 5 years, the CO2 is reworked. Have in mind this photo from outside. 71% of the Earth's surface are oceans. So this is the key to climate understanding. So I mentioned already that during mountain building and based on plate tectonics, we have a very huge volcanic activity. And what we know the volcanoes, yeah. The Etna is emitting at the moment, but there are a lot of undersea volcanoes. Let's say I mentioned the Circum-Pacific Fire Belt and all the other mid-ocean ridges with volcanic activity. These are 65,000 kilometers of volcanic activity emitting CO2, vapor, whatever. Alone the Atlantic, you see that in this graph from the Arctic to the Antarctic, this mid-Atlantic ridge is 20,000 kilometers long. And you see all these volcanic activities emitting CO2 and also SO2. And what is, you can imagine, you see when Africa and South America had been together, they had been together. But since then, in 200 million years, they spread it away from each other. And these are 5,000 kilometers of volcanic rocks in the underground below the marine sediments nowadays. You can imagine what kind of volcanic activity that was. So this is the reason why CO2 is going up. And the anthropogenic input is less than 5%. This is the fact. And as I said, the oceanic pump also can release CO2 when the ocean water is warmed up, like since the end of the Little Ice Age. Just to show you the Etna. The Etna emits around, or many thousands of tons of CO2 into the atmosphere every day when he is active. And in 2022, we had a submarine volcanic event that was tremendous. And due to the very hot lava eruption, the water in the ocean, the depths of the ocean, started boiling. And so a huge volume, let's say, great volumes of water vapor went through the ocean to the atmosphere, increasing the humidity of the atmosphere by 10%. So this is affecting the climate and, of course, locally the weather. If we study a relationship between CO2 and climate or temperature, there is no relationship over the last 4.5 billion years. But in single cases, as we see here, you have the CO2 lagging behind the temperature and behind the temperature development. Let's say hot oceans release CO2, cold oceans absorb CO2. And you see this very nicely from one geoscientist in, let's say 237.500 years ago. You clearly see the CO2 goes behind the temperature. And there are publications, scientific publications, stating that this time delay is sometimes hundreds, 600, 700 of years. So, just to finish, it's a little bit later, I'm sorry. Let's say the development and distribution of the Earth's different climate zones is constantly changing due to temperature changes. And this depends on the solar energy reaching the Earth, depending on the pulsating sun. And one thing is the pulsating energy leaving the sun. The other point is what gets to us on Earth. And this depends on the astrophysical parameters, on the form of the orbit around the sun, on the inclination of the Earth's axis and others. Then we also have an influence of the Milky Way galaxy with the cosmic radiation, as I explained, and of course the distribution of oceans and continents depending on plate tectonics are also very important. For that reason, in the northern hemisphere, we have much more continents than in the southern hemisphere. And so it's also difficult to compare the climate development in the southern hemisphere with all the oceans to the northern hemisphere with the most continental distribution. Yeah, and important are the heat storage of the oceans and controlled by oceanic oscillations. And what is very important, the atmospheric air currents. So the Earth is no greenhouse. It's an open system. So just to resume in one sentence, the aerothermodynamic system of the atmosphere is in natural equilibrium with a continuously varying insolation, controlling the climate through the influence of the oceans, which represent almost 71% of the plant surface. This is the natural sun-ocean atmosphere system. And there is no space for CO2. Sorry. Thank you for your attention.